1 again is the start to chapter 3. Chapter 3 is exponential and log functions and equations. So eventually we're going to go through and solve these equations, graph exponential and log functions. In 3.1, it's all exponential. So we're literally just going to get a head start on tomorrow, and that is do maybe one example actually, and then stop. So it just starts with the definition of an exponential function. An exponential function has a base a, and it's denoted by f of x equals a to the x. The biggest thing is that now our exponent is going to have the variable. That's how we know it's an exponential function. Okay. Our base is going to be it could be a whole number, it could be a fraction, it could be positive, it could be negative because there could be something like a negative on the front of it. And then the exponent, we're going to start to build on it. It's going to just be a variable. Then it's going to be a variable with a horizontal slant, a horizontal shift and all those things. The biggest thing is that a itself is going to be positive. There could be a negative added to the front, and if it does, it flips my function upside down. Okay, but the base will be positive. And it won't be 1. If I took 1 and I kept raising it to a power like 1 to the second, 1 to the third, 1 to the fourth, 1 to the fifth, what happens to that? It stays the same. And if I have something in which my y value stays the same, it's a horizontal line. That is not an exponential function. An exponential function has some sort of growth or decay. We start with just the calculator portion of it, which your test will have calculator and non-calculator. It says evaluate the function at the indicated value of x and then round your answer to 3 decimal places. So if f of x equals 0.5 to the x and x is 1.5, then depending on your calculator, you're literally going to do 1.5, and then you could do your little caret. 0.5, and do your little caret to the 1.2. And I get 0.4352. It says to round answers to 3 decimal places, so it's 0.435. And then B just builds on it. 150 times 2 to the x, and x is negative 2.5. 150 times 2 to the negative 2.5 is what I'm going to type in the calculator. Be careful and don't group together 150 and 2. Only 2 is raised to the exponent. So on our graphing calculators, we can literally type that all the way in 152 and then caret negative 2.5. Make sure that the negative is your leading negative, not the minus sign. And you should get 26.5165. So this is going to round to 26.517. Questions on either of those? If you are using, let's say this is where the calculator on your phone gets annoying. If you're using the calculator on your phone to do this, then you have to do just this part first, and then you have to multiply it by 150, okay? Or you have to put your parentheses in, which sometimes is where it gets annoying. Your handheld is perfectly fine. Like, it'll do it in the right order. Okay, we're going to jump all the way to the second to the we're going to pick up with graphs of exponential equations. So first of all, the domain of every exponential equation is all real numbers, okay, or negative infinity to positive infinity. Because there's nothing we can't plug in to an exponential function. In your parent exponential function, your y-intercept is 0, 1, because in every, like if I just did f of x equals 2 to the x, or 3 to the x, or 1/2 to the x, and I plug 0 in for x, what happens when we raise something to the 0 power? It's 1, okay? So in the parent function, we're not saying this is every exponential function, but in the parent function, my y-intercept would be 1. Anything else, we'll just plug 0 in for x, like we do every other time we're finding the y-intercept. B is the base on the exponential function, and if b is greater than 1, then that graph increases. So that would be something like the blue graph that's in the little right corner. God bless you. This would be what an exponential graph looks like if the base is a whole number bigger than 1. If b is in between 0 and 1, so now our base is a fraction or a decimal between 0 and 1, then it decreases, so it would look like the pink one that's in that bottom right corner. The graph is 1 to 1. It would pass your horizontal line test. It would pass the vertical and horizontal line test, so it's a function and it's 1 to 1. And the parent function has a horizontal asymptote at y equals 0. That horizontal asymptote is going to shift with a vertical shift. Okay, so the horizontal line moves up and down if there's a vertical shift on our function. So it starts at y equals 0, but if I shift this graph up or down, then my horizontal asymptote shifts with that vertical shift. So we're going to learn how to graph these by hand, and then we're going to also learn how to graph something with an e base, and that we'll use the calculator for. So example 2 says graph the exponential function. When you do this today and when you do this on your test, I'll give you a little t-chart to plug in, okay? So I can start with my common ones, which would be -1, 0, and 1, and then I plug it in. 3 to the -1. What happens when I raise something to a negative exponent? It moves it to the bottom, so this becomes 1 over 3. 3 to the 0, we said anything to the 0 power is what? 1, and 3 to the first would be 3. Oh, this is 1/3. I wrote 3 there, 1/3. Okay, so now I'm going to go to my graph and I'm going to plot this. At -1, it's 1/3. At 0, it's 1, and at 1, it's 3. It's not going to cross the x-axis, so I hug the x-axis with the left side of this curve. And then it's going to increase exponentially, so it has that curve to it. I'm going to run it through my 3 points. So in addition to graphing, it's going to ask you for domain. It's going to ask you for range. It's going to ask you for your y-intercept. And it's going to ask you for your horizontal asymptote. What's the domain of every exponential function? All real numbers, so -infinity to +infinity. What's the range on this function?
1/3 to infinity.
So 1/3 is the lowest one we got, but it would keep going, right? What's it not going to hit? But get close to 0, and we don't include it, so it gets a parentheses, 0 to +infinity. What's your y-intercept? 0, 1, which you can either get from your graph, but also if you use these points, it's that center point. And where do we say the horizontal asymptote is? Y equals 0. Questions so far? So this would be on the open-ended portion of your test, and it's going to have multiple parts like that. All right, now we go to B. So I'm going to plug in the same points. And this time my exponent's a -x, so I'd get 3 to the -1 minus 1. -1 becomes what? +1, so this is 3 minus 1, and I get 2. Then I plug in 0, 3 to the -0 minus 1, which is still 3 to the 0, or 1 minus 1, and that's 0. And then I get 3 to the -1 minus 0, minus 1, which is 1/3, minus 1, 1/3 minus 3/3, which is -2/3. So I plot these, -1, 2, 0, 0, and 1, -2/3. So clearly we're decreasing as I fall to the right. This would mean it's decay. Like if you compare this to growth and decay models, if it's increasing, it's growth, and if it's decreasing, it's decay, which is this. And we've dipped below the x-axis this time. I said it before, but just as a reminder, your horizontal asymptote moves with a vertical shift. So that -1 after the function took my horizontal asymptote, which was at 0, and it just shifted it down to 1, or to -1. So that's consistent with my graph falling as I move to the right. It gets close to, without touching, -1. So let's answer all the questions again. What's domain? All real numbers. What's range? Good. -1 to infinity, and -1 gets a parentheses because we can't include it. What's your y-intercept? Y, or 0, 0. Good. Again, from the graph or from the center point on your t-chart. And where do we just shift our horizontal asymptote to? Y equals -1. Good so far?
Yep.
So again, something you'll do by hand just like that on the test. All right, so think about all the transformations, because sometimes we can use transformations to draw the graphs. Everything that has your transformations, just like every other graph, has the same effect. All right, so transformations, if we are adding or subtracting after the function, so after means not in the exponent this time. If we're adding and subtracting, it's a shift up and down, same as usual. If you're adding and subtracting in the exponent, that's like it being inside the parentheses or inside the absolute value or under the square root. This shifts left to right. Positive goes left, negative goes right. If you have a negative on the front of the B or the front of the base, it reflects it over the x-axis. So it takes my function that normally looks like this, and it's going to flip it upside down. And then if there's a negative in the exponent, it flips it over the y-axis. So instead of going up and to the right, it flips it the other direction. So it flips it right to left. Top one flips it upside down. Bottom one flips it left to right. Then you've got your vertical stretch and your shrink. If you are multiplying something on the front of your term, then it's a vertical stretch if it's bigger than 1, and it's a vertical shrink if it is less than, or in between 0 and 1. And last but not least, if the exponent has your stretch or shrink, if that is bigger than 1, it's called a horizontal shrink, but it makes it more narrow, just like a vertical stretch. And if it's in between 0 and 1, it's called a horizontal stretch, but it makes it more wide, just like a vertical shrink. I would say don't worry too much about the vertical stretch and shrink, because you can always plot a point to see what's happening, but you definitely want to understand your shifts. And remember that the vertical shift is what moves the horizontal asymptote. All right, so now we're going to use the graph of f of x equals 4 to the x to graph these. So the graph of f of x equals 4 to the x, if I had plugged in points, -1, 0, and 1, would be 1/4, 1, and 4. So my parent function would be -1 and 1/4, 0 and 1, and 1 and 4. It would look like this. So instead of making a t-chart for each of these, let's talk about what our transformations would be. What's going to happen to the graph for A?
Up 3.
It shifts it up 3. So instead of being at 1/4, we're at 3 and 1/4. Instead of being at 0, 1, you're at 0, 4. And instead of being at 1, 4, we're at 1, 7. Good. And our vertical asymptote went from 1 to 3. Does it change your domain? A vertical shift? No. Does it change your range? Yeah, so domain is still negative infinity to positive infinity, but range this time is now 3, positive infinity. Y-intercept became 0, 4, and the horizontal asymptote went up 3, so it's y equals 3. All right, B says g of x equals 4 to the x minus 2. So what's happening in the x minus 2? What does that cause? Horizontal shift, good, right 2. So all my initial points, which were at 0, 1/4, go to the right 2. Then 0, 1, it goes to the right 2. And then 1, 4 goes to the right 2. Does a shift to the right move my horizontal asymptote? Nope, it's still at 0. Does it change the domain? Nope, negative infinity to positive infinity. Is the range changed from my parent function this time? No, it's still at 0 to positive infinity. Okay, my y-intercept, I'd have to find it by plugging 0 in. So if I plug 0 in, I get 4 to the negative 2. What's that? Good. And my horizontal asymptote is still at y equals 0. Questions on those? All right, the one-to-one property, this is something that we're going to use now, and then it's going to keep coming back in each section after this. But the one-to-one property says, for a being greater than 0, so our base is not negative, okay, and it not equaling 1, a to the x equals a to the y if and only if x equals y. And basically all this means, if I have two numbers raised to the same, or with the same base, so my base has to be the same. If the base is the same, then I can literally ignore the base and set my exponents equal to each other. So if it said 1/7 to the 2x equals 1/7 to the 8th, then I ignore the base because the base is the same, and I would set my two exponents equal to each other. Now, sometimes the bases are already equal to each other, and sometimes we have to work to rewrite a base so that it is the same, which is what you'll see in a second. And again, remember, anything to the power of 0 is 1. We already talked about it today, but it's definitely going to start to come back up. All right, so example 4 says solve, and it says using the one-to-one property. Eventually, it will just say solve. So I'm going to go to A. Are the bases the same? No. Can I rewrite them so that they are, is the question. Yes. So instead of changing 3, I'm going to change the bigger one to be a base of the smaller one. So the 3 to the x minus 2 is going to stay the same. But 9 is 3 to what power? Good. So I'm going to rewrite 9 so that it has a base of 3. And then I'm going to ignore the bases because they're the same. And I'm going to set my exponents equal to each other and solve for x. Now these are easy to check because I could literally just plug it back in. So 4 minus 2 would be 2, and 3 squared is 9. Now go to B. Are the bases the same? No. So one's a fraction and one is not. There's a couple different ways to do this. One is, if you don't like the fraction, change the fraction. So if I wanted to move the 2 from the bottom to the top, how do I do that? A negative exponent. So 1/2 is the same thing as 2 to the negative 1. That's still raised to the x power. So on the left-hand side, this would be 2 to the negative x. Now on the right-hand side, I want the base to be 2. If you know it off the top of your head, rewrite it. If you don't, break it down until you get to all 2's, and then count them. 1, 2, 3, 4. So this is the same thing as 2 to the 4th. And now the bases are the same, so we ignore them and we set our exponents equal to each other. Multiply or divide by -1, and I get x equals -4. Questions on that one? Okay, and then the last one, 6 to the x equals 1. What did we say the power would be to get a 1? 0. There's no way to figure that out other than to memorize that property. You can't 0 root something, okay? So just make sure you have that memorized. Everybody still with me? Okay, so now we switch to the calculator-based questions. Okay, E is called the natural base. So E is a variable that represents a number, just like pi or something like that, okay? We call it the natural base because if I took, so hopefully this looks somewhat familiar, this is like your interest question, except the N or the R, no, the number of years is just T, would be just 1, okay? If I took a number and I added something to it and I kept raising to a power, it eventually levels off. So you don't need to ever fill in this chart. Just know that it's not like a made up number. E didn't just like sprout from the ground one day. They actually, somebody with lots of time on their hands, followed the patterns of numbers and said, what happens if I take this and I make n get bigger and bigger and bigger and bigger and bigger, and by getting bigger and bigger and bigger and bigger, we mean it would be exponential, okay? It eventually gets to a number in which there's such a little difference, okay, that we would always round this. So it rounds to 2.72 if I shorten it, okay? Technically it's 2.78 there at the end. But we round E to 2.7 if we're going to just use 2 digits, 2.72 if we're using 3. So when you're looking at E, you can, like, let's say I'm graphing it or something like that, you can almost say it's like if it was 3 to the x. So it has the same behavior as something that has a base of 3, okay? It is more specific, and your calculator has an E button, and that's what we will use, okay? The calculator has it saved as, like, the actual number that doesn't end, okay? But it is called the natural base. So every time you see E, we're talking natural base. So we can use it in expressions, and usually exponential expressions. So this one says, use a calculator to evaluate the function f of x equals e to the x at each value of e, and then round to 3 decimal places. So your E is above the ln button. It's on the left-hand side of your calculator. If I want to find e to the 4.2, I do second ln, and it brings up the e, and in the exponent, I just type 4.2. And we're going to round this to 3 decimal places. 66.686 would be how that rounds. God bless you. B says 125 e to the 0.05x, and x is 30. So I literally type in 125 e to the 0.05 times 30. And your calculator can do all of that at once. 125 second ln 0.05 times 30. Just be careful. Make sure you put the decimal in the right spot. This is 560.211. Oops. So if you know how to use your calculator, you know how to do these, right? And you type them in carefully. These would be on the calculator portion. So you're going to get stuff either with the E as its base or with an exponential function as its base, and it's going to ask you to evaluate it at a specific point.
Would you just write the number? Or would you...
So these on your test are multiple choice, but you would just write the number. Yeah. Still good? Okay. Homework that you get something like 2.3, let's say, e to the negative, I don't even know, 64. We talked about this, right? If it says e to the whatever, what does this mean? It's like scientific notation. That's like 2.3 times 10 to the negative 64. And what does that tell you? If your exponent on the 10 is negative, what's it mean if it's in scientific notation? This is a great sign. Do you know what scientific notation is? If this said 2.3 times 10 to the negative 3, what does that mean? It means you move your decimal to the left 3 places. Isabella, get your head up. 1, 2, 3. And so there would be 2 zeros in front of that 3. So if it had said 2.3 times 10 to the negative 64th, what does that mean? It means there's 63 zeros in front of this sucker, and if I'm going to round it, it's going to round to what?
Please report to students.
0. Now we're going to graph E. But what did we say E would be like? If I wanted a whole number base. It'd be like 3. So if I were to just like look at functions, let's say, if I were to just look at multiple choice, and I didn't have the calculator to actually figure out these points, I would say 3 to the x would be my base, right? So it's going to have my original exponential shape. The 4 would make it grow faster, so it would make it narrow, and the plus 2 in the exponent would shift it left 2. So if I was just to compare my parent function, that's what it would look like. With a calculator, I will just plug in points. So I'm going to set up a table, -1, 0, 1. We're going to plug in points, and then we're going to actually graph it with the graphing utility to check it at the end. So the first one I'm going to do is 4e to the -1 plus 2. Then I'm going to do 4e to the 0 plus 2. And then I'm going to do 4e to the 1 plus 2. So this is 4e to the first, 4e to the second, and 4e to the third. This is 10. I'm only going to round to 1 decimal place because we're not going to get more accurate than that on the graph. 10.9, 4e to the second, 29.6, and 4e to the third, 80.3. So I'm going to go by 5s here. 5, 10, 15, 20, 25, 30. And I know 80 is going to be all the way up here. Okay. So -1 and 10.9. 0 just shy of 30. And 180. So from the points I plugged in, I never got it to flatten out. And this is where your knowledge of exponential functions has to help you out. Is there a vertical shift on this thing? No. So where is my horizontal asymptote? It's at 0. So I still need to be able to take these points and flatten them out, okay? Normally it flattens out over here, right? But because I took this graph and I shifted it 2 points to the left, it shifted it that way. My y-intercept is still that middle part of my graph, so it would be 0 and 29.6, which is also here, okay? But that's what it looks like. Yep.
So the stretches and shrinks don't really like do anything?
I mean, they do. If I had done this by ones, it would have been really, it makes it grow faster. That's what it does. And if it was a 1/4, it would flatten it out. Yep. All right, now actually use your y equals. So use your y equals and type in 4e to the x plus 2. All right, so again, I did y equals 4 times e to the x plus 2, and then I graphed it, okay? So it's similar to what I see, but because I'm cutting it off at 10, I don't see my y-intercept or anything like that. Questions? Slide, and we're going to talk about compound interest. We're going to talk about just part 1. Huh? We'll go back to graphing tomorrow. Graphing, it takes a little bit longer. So compound interest versus continuous compound interest. If you've ever put money into an account in which it earns interest, or you ever used a credit card in which it earns interest, let's say a savings account, this would be good interest, right? You're making money on your money. Whereas credit card is bad interest. You're being charged money on the money you're borrowing from your credit card. These interests are compounded in different ways. One is a certain time of year. So if it says that the interest is compounded monthly or compounded daily or compounded annually, okay, that would be a number of times per year. And for that, we use the formula P, which is the principal balance, the thing whatever money you put in, times 1 plus R over N to the NT. PERT is continuous, and that we'll go back to tomorrow. PERT means that it's being compounded so frequently that we can't say it's by the minute or by the sec or by the hour, okay? It's literally just continuously being compounded. For savings, that would be good because you're earning money faster. For interest on a credit card, that's the worst because that means that it's literally, which is how it's usually done. It means it's literally being compounded every second. So if I put $5 in an account and I'm compounding daily, for example, if I put $5 in an account at the end of the day, I'm earning whatever percent on that $5. So if it's $5 and I'm earning 10%, okay, I'm earning 50 cents at the end of the day. Then I keep going, okay, 5 cents. 5 cents, move your decimal twice, okay? No, I was right the first time, right? Trying to do this without writing it down is making my head dizzy. If I had, let's say if I had $5 in the account, what's 5%, what's 10% of $5? 50 cents. So at the end of the day, I'd now have $5.50 in the account. Then at the end of the next day, I'd earn another 10%, which is now 55 cents. So I'd have $6.05, okay? You don't have to figure that out because we have a formula that does it for you. If it's compounded annually, then our N is 1. If it's compounded semi-annually, then our N is 2. If it's compounded monthly, what is N? 12. If it's compounded daily, 365. It's compounded weekly, 50, 52. There's 52 weeks in a year, okay? PERT, we will come back to tomorrow because we'll talk about E, but that's compounded continuously. Again, not a specific number of times a year. All right, so we started already with compound interest happening a certain number of times a year. So if it says daily, weekly, monthly, quarterly, semi-annually, I use that first equation. A equals P times 1 plus R over N to the NT. If I want to figure out compounding continuously, which again is like so frequently, it's not a specific time, then I call it PERT because that's how it's spelled. Okay, A equals P times E to the RT on the calculator portion of your test. Okay, so it says find the accumulated value of an investment of $15,000 a year, or $15,000 for 2 years at an interest rate of 3.2% if the money is compounded semi-annually, quarterly, monthly, and continuously. So 4 different questions. If it's semi-annually, how many times a year is that? 2. If it's quarterly, it's 4. Good. If it's monthly, it's 12. And if it's continuously, we're using PERT. So for these 3, we use P times 1 plus R to the N, R over N to the NT. The 15,000 is our P. 2 years is T. And the rate being 3.2 means R is what? 0.032. You got to move your decimals 2 places to the left. So for semi-annually, it'd be 15,000 times 1 plus 0.032 over 2 raised to the 2 times 2. One of those 2's is for the N, and one of those 2's is for the years.
What's N?
The number. All right, I'm going to record it. So obviously, you hopefully know how to type it in the first time, but we'll show you how you can reuse it. So 15,000 times 1 plus 0.032 divided by 2. You can put the fraction in there, but you also don't need it because order of operations is going to say divide, then add, which is what we wanted to do. 2 times 2. So for the first one, for semi-annually, I get 15,000, and it's money, so we're rounding to 2 decimal places. I get $15,983.29. Now I want to change it to quarterly. If you arrow up and select your equation, it will duplicate it. And the only thing I need to change is the 2 goes to a 4. And in the exponent, one of the 2's goes to a 4. So for B, you've got $15,987.31. And then I'm going to do it again. Arrow up to the equation. And this time I'm changing my 4 in the bottom It's a 12. So I'm going to do 1 to take the 4, and then second insert gives you a space to fill in. Otherwise, it's going to take over the parentheses. And then instead of the 4, it's 12. And I get $15,990.02. And then continuously 15,000 times E to the 2 times 0.032.
Wait, N is
And is number of times a year.
and then
So for continuously, it's P, which is 15,000, times E to the RT 0.032 times the number of years, which is 2.
what was A?
A is $15,983.29. So if you had gotten asked more than one of these questions and you compare them, it should make sense that the more often we compound it, the more money that you're making, okay? So our biggest always should be PERT, like if you're comparing it because it's compounded the most. But obviously if we're doing 2 to 4 to 12, the money should increase. It shouldn't increase like rapidly, but it should increase a little bit, okay? The no longer we keep it in this account, so the higher that T value is, and the higher the rate earned, obviously the more money it grows. But like, use your common sense here. If you start with 15,000 and it's in there for 2 years, it shouldn't jump to like 50,000. Something's wrong, okay?
A had 52,000.
Look at